We've already learned about the theory of UV-Vis spectroscopy. Now, what do we do with it? Well, one of the things we can do is if we have a solution, all right, and in general, what we have in UV-Vis is we're going to have a cuvette, all right? Now, one of the things that normally confuses students is when you get to this point where you can actually generate an equation and you solve for things, there's something in Beer's law that always confuses people. All right. So Beer's law basically says that absorbance by something in this sample is equal to the molar extinction coefficient given by epsilon. Sometimes this is also called molar absorptivity times the path length of the cuvette times the concentration in the sample, and then I'm going to put this in parentheses plus a y-intercept, and that's assuming that in the sample that you're running in the lab, you have a y-intercept. In most cases, you have a small y-intercept. In theory, you shouldn't, and that's because at zero concentration, there should be zero absorbance. But in reality, there usually is a very small contribution from the y-intercept. All right, but this is basically the Beer-Lambert law, or sometimes shortened to Beer's law. All right, now this epsilon, okay, at times L. This right here, and we went over this in another video, this right here is the slope of the line. Because when you multiply these two numbers together, they're not functions, they're just numbers. So this is actually, when you multiply these, this is a constant, all right? So whenever you generate a curve, oops, let me get that back. Whenever you generate a curve in Excel or numbers, you always generate it in the form y is equal to mx plus b, right? Well, you have Beer's law. It says a is equal to epsilon LC plus b. Well, you should ask yourself one thing. What in my Beer's law is the dependent variable, and what is the independent variable? Well, the independent variable is the thing that that changes and affects the dependent variable. Well, the thing that I change is the concentration. Well, in a linear regression line, that corresponds to x. So it turns out that anywhere in this y equals mx plus b I see an x, I'm just going to replace that with c. All right. Now, one obvious thing is that the y-intercept is just the y-intercept. Okay, that's the y-intercept. Okay. Now, in terms of this over here, this should also imply that absorbance is the dependent variable. And in fact, absorbance is the dependent variable. Okay. So a corresponds to y, but then you have this problem. Okay. Whenever I have a y equals mx plus b, right? So here's y, here's x. I just get a straight line, right? I get a straight line. And we know that when you have something with a constant slope, the slope, m, should just be some number, right? It could be 3, 5. It's not a function, it's a number. But here I have two things. I have epsilon times L. Well, it turns out that whenever you take m, the slope that you get from the linear regression line, that's just equal to the extinction coefficient times L. So what is known in this? You have to ask yourself what is known. Well, the m is just going to come out of the line that you generate, and that's going to become more clear in a few minutes. M, so you know that. The path length and the extinction coefficient. So you have two variables, right? Well, it turns out that you don't. L is actually known. And it turns out that for probably every single cuvette you're going to use in your life for UV-Vis spectroscopy, the length of this cuvette is exactly 1 centimeter. All right, this length right here, and it's square on each side, right? But the length on each side is 1 centimeter, okay? I can tell you this just from experience. The place that I got my undergraduate degree, every single spec machine we use, and there were 3 types. There was a little cheaper one. There was one that was like this big kind of green machine you could put on the desktop in the lab. And then there was like a really high-tech one in the instrumental lab. Every cuvette, didn't matter if it was a quartz cuvette, plastic cuvette, they're all 1 centimeter. I go to my grad program, they're also 1 centimeter. They're just all 1 centimeter. So L, unless they tell you otherwise, is 1 centimeter. So I know both these things, and then what I'm going to do is I want to find epsilon. So I'm going to divide both sides by L, and it turns out that epsilon is just equal to the slope that I generate from this line, and I'll show you how to do that in a little bit. It's the slope, and then I just divide by the path length. And that's the magnitude of this extinction coefficient. It turns out that this extinction coefficient is going to be very important to find, because that's how you determine things in the lab. You need to know this extinction coefficient. Now I'm going to tell you how you do that. So just remember, I'm going to have some sample inside here in the cuvette, okay? And then in the machine, I have a light source, right? The light source of the spectrophotometer is going to shine light of a specific wavelength, and usually, well, in this case, it's going to be in the UV-Vis range. Some of this light will get absorbed by the sample, a little bit of it, some fraction might go through it and not get absorbed. But remember, this sample is absorbing some of this UV-Vis light, okay? And that absorbance is what we are indirectly measuring, okay? So, whenever the machine, it's going to measure the light that's transmitted through, because it's actually measuring transmittance of light, and then through some formula that we're going to talk about later, it converts transmittance into absorbance. And absorbance is what pops out on the machine. That little number, that unitless number, that's the absorbance. Now, what do you do with this? All right, so here's my data from actually a lab that I did, okay? This is a lab I did in the biotechnology master's program when I was in that. So what I was measuring in this, this lab is I was measuring a protein called BSA. That's called bovine serum albumin. Okay, we actually have a form of albumin, but this is bovine. It's from cows. And it had some concentration that was in milligrams per milliliter. And it turns out that BSA absorbs at about 280 nanometers, which is in the that's in the UV part of the spectrum. So what I'm going to do is I'm going to get concentrations of BSA, and the concentrations are going to be as follows. The first sample is going to be 0.02 milligrams per milliliter. The next one's going to be 0.05 milligrams per milliliter. And I'm going to go all the way up and make all of these concentrations, okay? That's something that ultimately you will do using the dilution equation, and that's explained in another video, all right? So you use the dilution equation from a stock solution to get these concentrations, all right? And you're going to have different containers with a solution of each of these concentrations. So if I had 8 solutions here, I'd have to have 8 different containers to hold each of these, okay? Then what I'm also going to do, and I'll show you this, I'm also going to use DD water. That's also called, it's doubly distilled water. You can use milli-Q water. That's another thing you can use. This is a blank. The reason you use a blank is because there are some things sometimes that you put into the cuvette, you think you're only putting in your sample, but there are sometimes things can go into there. Sometimes the buffer you use may have a little bit of absorbance. Okay, sometimes there's things in the DI water or milli-Q water that absorb a little bit too. You need to account for that because you're not actually, you're not trying to measure the water. You're not trying to measure things in the water. You're not trying to measure the buffer. You're trying to measure BSA, the protein. So what you need to do is run a sample with 0 BSA and only water. And so therefore the concentration of BSA is 0. There's no BSA, it's just water. I also run one of the buffer. Okay, in this case I did have to use a buffer because BSA is a protein, and if you've taken biochemistry, you know that proteins have to exist in a buffer, otherwise they can denature. The buffer, it's pure buffer in there. So what's the concentration of BSA? It's 0. So all of your blanks, no matter what kind of blank you run, they should have a concentration of 0 of whatever you're measuring. All right, and then you're going to measure the absorbance of those. So essentially what happened is I basically took doubly distilled water, or milli-Q water, and I put it into the Spec machine, as shown right here on the paintbrush. I put it in here, I ran the Spec machine, some light was absorbed, some was transmitted through. The amount that was transmitted was converted to absorbance, and it turned out that doubly distilled water absorbed 0, had an absorbance of 0. That actually makes sense because it's completely pure water. Water does not absorb anything at this wavelength, 280, so you should get 0. Now, then I ran the buffer, all right? The buffer also has a concentration of 0. I got an absorbance of negative 0.006. That's fine, even though it doesn't make any sense, because what you can do with this buffer is, with this blank, there's a way you can do this on all spec machines. You can zero the spec machine. So that's what I say. This absorbance was set to 0. This just means that from now on, whenever I run these samples, I'm going to add onto it absorbance of 0.006. Why do I do that? Why do I add 0.006? Well, the machine automatically does that when I zero it, because it turns out that apparently the buffer, for whatever reason, when I just measured the buffer, it produced an absorbance of negative 0.006. But I want the buffer and everything over here, the buffer, to not have produced that contribution to the absorbance. So I'm going to add 0.006 to all of this, okay, so that this effectively becomes 0. All right? All right, so then what I'm going to do is individually I'm going to put all of these solutions, usually if it's possible, I'm going to put them all in different cuvettes, and I'm just going to put them in the spec machine and measure them. Okay, so apparently I did this first one of 0.02 milligrams per mil. It produced an absorbance of 0.025, so I'm just going to record that in my notebook, and then I'm going to take it out. I don't have to run another blank, it's already blanked. And then I'm going to put in this 0.05 milligrams per mil BSA. It produced an absorbance of 0.030. Fine, record that in my notebook. I do the third sample. It has a concentration of 0.1 milligrams per mil of BSA. Put it in the cuvette, run the sample. It produces an absorbance of 0.061. Record that in the notebook. So actually, once you get all the samples made, this actually becomes very methodical. Okay, you just put each sample in the cuvette, run the cuvette through the spec machine, measure the absorbance, all right? Okay, so I have 8 samples here, right? So now what I'm actually going to do is I want to basically take the concentration and the absorbance and plot them against each other, okay? So this is what I do. On Mac, on Mac numbers, which is like Excel, in fact, you do the same thing on Excel. What you're going to do is you're just going to highlight all these points that you want. Oops, that did not work. So let me go ahead and do this. There we go. So somehow you can figure out how you can just highlight all the points. Then what you're going to do is, and I don't have it visible on here, generally what you want to do is there should be an insert, okay, or something, and you're able to generate a chart. Okay, there's a way to do this on Microsoft Excel. You're actually going to generate what's called a scatter plot, okay? In this case, for Apple numbers, I'm actually going to do a 2D scatter plot, but in general, it's just going to say a scatter plot on, it'll say a scatter plot on whatever you generate, all right? So this is what comes up. Now, this data right here, it appears to be pretty close to a straight line, okay? There are some deviations, and that's normal. One thing I also do want to make sure that I do, I also want to label my axes. So this is the x-axis, okay? I want to put an axis name on the x-axis. This right here, recall, was concentration. So I'm doing this quickly. I would normally write out concentration, but that's not the important thing here. It is in milligrams per milliliter. Oops. Okay, there's that. I then also want to switch to the y-axis and also put an axis name there. This is going to be the absorbance. And absorbance is unitless. Okay, absorbance has no units, all right? Then what I'm going to do is I'm going to highlight this. What I want to do is go to series. In Microsoft Excel, this is usually on trend line. Okay, so what I'm going to do is I'm going to come over here, and there's a way on Excel to do this. You're going to say you want to basically plot a linear curve. It's not actually a curve, it's just a line. And what it's going to do is it's going to generate a line of best fit, okay, that fits the lines as close as possible to minimize the standard deviation. Okay, that's what the purpose of this is. Now, 2 things you want to do. You want to show an R-squared value. The R-squared value, this is called the coefficient of determination. And what it is it's a measure of ultimately your precision, okay, the measure of your precision. Okay, how good were your concentrations, assuming the machine was perfect? And it turns out I get a value of 0.9983. Now, R squared ranges between 0 and 1. If you had an R squared of close to 0, that's a terrible experiment. You need to redo it. So generally, that means you want to have an R squared that's close to 1. Truly, experimentally, you can never have an R squared of 1, but you can get really close to 1. And generally for these spectrophotometric experiments using Beer's law, usually an R-squared of 0.98 or above is pretty good. If you get that, you're doing really well. It's pretty good technique. This is 0.9983. That's decent enough. And then what I also want to do is show the equation. All right. So the equation that I generated is this. All right. So what I'd like to do is copy that onto Paintbrush. So 0.5694. All right. So this is, so let me get the white marker. So 0.5694. So y is equal to that times x plus a y-intercept, right? What's the y-intercept? 0.0082. So plus 0.0082. Now, remember what we talked about. Okay, let me move this back over here. Remember, the y corresponds to absorbance. The slope, which is just this number right here, 0.5694, corresponds to epsilon times L. X corresponds to the concentration, and the y-intercept is the y-intercept. So what I'm going to do to this is I'm actually going to rearrange this and put this in a much better form for the particular experiment. Absorbance is equal to 0.5694 times the concentration plus the y-intercept, 0.0082. All right? So, here's the thing. Every term here, because they're additive, has to be the same units as A. What are the units of A? It has no units, right? Which also means, because this term is by itself, this has no units, and this can also have no units. This can have no units right here, all right? So, what has to happen is concentration is usually in units of something like molarity, okay? If concentration were in units of molarity, what would the units of this number have to be in order to cancel molarity? Well, it would have to be 0.5694, and it would have to be inverse molarity, right? 0.5694 inverse molarity, because if you multiply inverse molarity times molarity, it becomes unitless. So that's how you determine ultimately the units of this part right there, all right? But you have to be very careful here, and this is the reason. What were the units of my concentration? They're actually in milligrams per mil. So you don't always have a concentration that's in units of molar. You can convert it to molar, but actually my concentration here is actually in units of milligrams per milliliter, which means that this number is 0.5694. It's actually going to be milliliters per milligram. That's just milligrams per mil to the -1. So milliliters per milligram, all right? So that's a very important thing. Now, remember, we want to determine the extinction coefficient, all right? So this is what we're going to do, all right? The extinction coefficient we have shown is the slope, this number, divided by the path length, all right? So it's going to be slope divided by length. The slope we just found was 0.5694 milliliters per milligram. All right. What's the length of the cuvette? The length is 1 centimeter. That's the length, 1 centimeter. All right. So that means the extinction coefficient is 0. Sorry about my cough. 0.5694 milliliters per milligram centimeter. All right. Now, one thing I'm going to go ahead and show you how to do is go ahead and convert this to what we usually say are the units of the extinction coefficient, which have to be inverse molar, inverse centimeter. These are really the units you want for the extinction coefficient because that's generally how it's always reported. So somehow I need to convert this. I need to convert this into units of inverse molar, inverse centimeter. Now inverse centimeter is already there, so I'm just going to worry about converting milliliters per milligram to inverse molar. Now what is molar? A molar is moles per liter, all right? So it's probably an indication I need to somehow convert the milliliters to liters, right? And then I need to convert the milligrams milligrams to moles. All right, now to do that, I actually am going to need the formula weight. I'm going to need the formula weight of bovine serum albumin. All right, so I went ahead and basically just looked this up for you to avoid the wasting time. The formula weight or molecular weight of bovine serum albumin is 66,500 grams per mole. So I need to convert this extinction coefficient to that. All right, so I need to convert this mils to liters. So I'm going to say there are 1,000 milliliters in a liter, right? I also need to convert this milligrams to grams because to get it to moles, this is grams per mole. So I'm going to say there are 1,000 milligrams in a gram. Notice here the milligrams end up canceling, the milliliters here end up canceling, all right? The last thing I need to do is just convert the grams to moles. I know it's 66,500, that's an approximation, by the way. It's actually a little bit less than that, but grams per mole, grams here cancel, and now what I need to do is go ahead and calculate what this ends up being. Now, one thing, let me just go ahead and tell you this, right? 0.5694 divided by 1,000 times 1,000, all right? 1,000, just go ahead and cancel those, and so this is going to be 0.5694 times 66,500, all right? So let's go ahead and do that. I can actually do that in Excel, and I'll show you how to do that. It's actually pretty easy. You do actually basically the same thing in both Excel and Numbers. Just pick any one of these little slots. You write an equal sign. In Excel, as far as I know, the one that I used to use, it doesn't come up with this little function thing, but in Numbers now it does. But all you do is you go back here and you say, well, this is going to be 0.5694 times 66,500. So this is going to be 66,500. To do times, you put this little asterisk, and then it puts a multiply in there for you. And then let me just make sure. I'm really bad at memorizing numbers, actually. 0.5694. So 0.5694, what is that? So this is your molar extinction coefficient, all right? So 37,865, all right? 37,865. So I am really bad at memorizing numbers. 37,865, 37,865. All right, now, notice we have centimeters in the denominator, so I'm going to have an inverse centimeters here for the unit, right? But notice I have a liter per mole. Well, a mole per liter is molar, but a liter per mole, that's inverse molar. So remember how I said we wanted the extinction coefficient in inverse molar, inverse centimeter? This does it. And so this is our extinction coefficient. Now, why is that useful? Well, that's ultimately useful because it really doesn't matter what extinction coefficient we use. If we report it, we generally want to put it in these units. But let's suppose I measure an unknown sample. It's still of BSA, but it's at an unknown concentration, and I want to determine its concentration. Well, if I know the y equals mx plus b equation, and I have a sample of unknown concentration, well, I can just measure its absorbance, right? I can measure its absorbance and then calculate its concentration using this curve. So what I'm going to do is I'm going to pick a concentration that I want to do. Let's say the concentration is 0.4. I didn't explicitly measure that. So let's suppose my absorbance that's unknown, I have an absorbance that's 0.40. And what is the concentration? Now remember, if I use this equation, concentration is going to be in milligrams per mil. Now I can go ahead and convert that to molar, but it will be in milligrams per mil. But that's still fine, all right? So how do I solve for concentration? Well, my equation is A is equal to, epsilon L times the concentration plus the y-intercept. So how do I find the concentration? Well, I need to first subtract B from both sides, the y-intercept. So I get A minus the y-intercept is equal to epsilon L times the concentration. And then I can go ahead and divide both sides by epsilon L. And that's going to give me that the concentration is equal to the absorbance minus the y-intercept divided by epsilon L. And remember that epsilon L is just the slope that you generated from that curve. So if I want to find this particular concentration, what's the absorbance that I had? The absorbance that I measured was 0.4. That's my experimental absorbance of this unknown concentration. What's the y-intercept? It's 0.0082, so minus 0.0082. And then I have to divide by epsilon L. Well, we found epsilon L was 0.5694. 5694. What were the units of that? The units of that were milliliters per milligram, right here. Milliliters per milligram. So this is milliliters per milligram, all right? So now I need to find out what my concentration is, all right? So let's go ahead and do that in numbers. So 0.4, let's just pick a random one. All right, so equals. I'm going to program this. I'm going to say 0.40 minus the y-intercept, which is 0.0082, I believe. Close parentheses, and then I have to divide by that extinction coefficient. And I am so bad at memorizing numbers. I really am. It's 0.5694 divided by 0.5694. And my concentration is apparently 0.688. About 0.688. Right? Let's see. So I am so bad. I apologize. 0.688. And since I divided by milliliters per milligram, this becomes milligrams per milliliter. And this right here, go ahead and box this because it's our answer. This is the concentration of our unknown sample. So usually the utility in finding that extinction coefficient is your extinction coefficient can actually help you determine unknown concentrations for a sample just by measuring the absorbance, because in theory everything should follow Beer's law. Now in another video we'll go over where there could be deviations from that, but in general in normal labs you don't have to worry about that so much unless you have super high concentrations, which is not normally likely. All right. One other thing I want to make sure you understand. There's two things here. All right. Remember, when we do this graph, okay, this is the curve I generated, this line that I generated from A versus C. When you do this, absorbance has to be on the y-axis, okay? Concentration has to be on the x-axis. It will be very different if you don't get that. You can actually still determine concentration, but that's not the standard of how it's done. A is always vertical, C is on the horizontal axis. Remember, the extinction coefficient, or this slope, I'll say that actually this slope right here, 0.5694 or whatever it is for your data, those units are dependent on the units of your concentration here, okay? So if your concentration is milligrams per mil, then this number will be in units of milliliters per milligram, okay? If your concentration on this plot was converted to molar, then this number will be in units of inverse molar, or 1 over molar, okay? A great example of that is shown right here, okay? Remember, for the extinction coefficient, if your concentration on that plot was in milligrams per mil, your extinction coefficient will be in milliliters per milligram per centimeter. If your concentration on that plot was in molar, then your extinction coefficient will be inverse molar, inverse centimeter. Okay? So you have to pay very close attention to what the units are on that plot, okay? And you have to use that when you calculate your extinction coefficient. But that's basically what you do. You're determining the extinction coefficient so that you can actually determine the concentration of an unknown sample given the absorbance that you measure for that sample. Now, before I let you go on this, there's a couple caveats that you have to understand, all right? When I say an unknown sample, notice here, I was measuring bovine serum albumin for the curve, right? For this curve, I measured BSA, bovine serum albumin. The unknown sample still has to be BSA, all right? It still has to be BSA. It can be an unknown concentration, but it has to be the same compound. The reason for that is because even at the same wavelength, this is 280 nanometers, right? Even at 280 nanometers, BSA will have a different extinction coefficient than paranitrophenol or any other compound. Compounds always have different compounds at different extinction coefficients at the same wavelength. So this is why you have to do it for the same compound. So if you're trying to determine an unknown concentration of nitrophenol, you have to do your calibration curve that we just did for paranitrophenol. Okay, and you have to determine the extinction coefficient for paranitrophenol. Same thing's true of any compound. The other caveat is that all of your measurements, both for the standard curve that we just generated and for the unknowns, they all have to be at the same wavelength. It's also true that if I change this wavelength even to 281, the extinction coefficient will also change. Okay, so that's a problem because then you're going to get an inaccurate concentration when you measure the absorbance if you change the wavelength. So the two caveats are, for a standard curve, the unknown has to be the same compound exactly, usually in the same buffer also, and the absorbance has to be set to be measured at the same wavelength. Okay? If all those things are satisfied, you're going to get an R squared above 0.98 if you have good technique, which is very good. All right, so hopefully this video helped you give you an intuition on how to deal with Beer's law using this. In another video, we'll go over how to deal with this for measuring enzyme activity. See you in the next video.